Welcome to GLNCDIO. Today we're flying a drone over one of the most extreme science machines on Earth, and letting AI tell us where it's broken. The 500-meter Aperture Spherical Radio Telescope, or FAST, China Sky Eye, is the world's largest single-dish radio telescope. Its reflector is over half a kilometer across, built from thousands of metal panels. If even a few panels get dented or damaged by falling rocks or debris, the telescope's sensitivity drops. Historically, teams had to physically climb the structure and visually inspect it. Slow, risky, and easy to miss tiny defects. So here's the question: how do you reliably find tiny defects on a huge curved surface without risking people's lives? The new answer: drones. Plus deep learning. Plus a clever feature fusion trick. 1. Turning FAST into a flyover dataset. Engineers mount a high-resolution RGB camera on a drone and program a precise flight path over FAST's reflector. As it flies, the drone records detailed video of the surface, tags every frame with centimeter-level GPS RTK location, lets us map each pixel back to a specific reflector panel. So instead of humans hanging off the structure, we get a structured aerial dataset, images plus exact coordinates for where each possible defect lives. Here's the catch: defects are tiny relative to the entire dish. Different defect types can look very similar. Traditional detectors compress features in a way that loses fine detail, especially when objects are small. Most object detectors fuse features from different network layers by simple addition or concatenation, treating every pixel the same. That's too coarse for FAST's surface, where one pixel might be harmless texture and the next is a hairline defect. Three, cross-fusion. Point-wise. Attention for defects. The team introduced a cross-fusion plugin, a lightweight module that sits inside standard deep detectors. Instead of fusing features layer by layer, it fuses them point by point, using an attention mechanism that asks, at this exact location, which layer's features matter most? Key ideas. Each pixel's feature in one layer becomes a query. Corresponding features from other layers are keys. The network learns how to mix high-level semantics with fine details differently for each pixel. Dilated pooling expands the context for low-level features without making the model heavy. Result: the detector gets sharper vision for tiny, subtle defects, with only a small increase in parameters and compute, which is crucial for drone-based workflows. 4. Why this matters for you as a STEM mind. With this AI plus drone pipeline, inspections become safer, humans stay on the ground. Coverage is faster, spanning the whole reflector quickly. Detection is more reliable, especially for small defects. The same techniques generalize to bridges, solar farms, runways, power lines, and more. You're not just looking at one telescope problem. You're seeing a template for how we'll monitor huge critical structures using aerial robots and specialized vision models. Your takeaway model. If you're a STEM student, think of this as a 3-layer pattern. Sensing. Drones capture high-resolution, geo-tagged imagery. Perception. Deep detectors with smarter feature fusion find defects. Action. Engineers use precise defect maps to plan repairs. Anytime you meet a giant structure, tiny failure problem, you can ask, what's my drone equivalent sensor? What's my cross-fusion style perception upgrade? How do I turn detections into decisions? I'm Rad2X from GLNCDIO. If you want more breakdowns like this, where we turn cutting-edge research into clear mental models and systems you can reuse, visit GLNCDIO and explore the GLNCDIO Knowledge Center for deeper frameworks, archives, and AI-ready study tools.